Okay, so last class I gave you what the kinematic equations were, right? That's what I mean by the Old Faithful, the Big Chalupa, and Got No Time. But I just kind of gave them to you. I didn't show you where they came from, and that's the point of this video, is to show you where the equations come from. So we're going to derive the kinematic equations. I'm actually pretty sure that derive only has one R, but whatever, we will get started. Okay, so we're going to start with, one of the things that's kind of neat about physics is that you can always, you can get to complicated results from very simple starting points. And what I want to do is I just want to talk about two things we've already defined. We said that the average velocity is equal to delta x over delta t, and we said that acceleration equals delta v over delta t, right? And then just as a reminder, we said that when I talk about v, v naught is going to mean the initial velocity, and then v is going to equal the final velocity, and a couple other things. Remember that delta v is going to equal the final velocity minus the initial velocity, and then you got v bar, which is going to equal the average velocity. Okay, so I'm going to start with these two equations, and then I'm going to try to get to the three other kinematic equations we talked about last time: Old Faithful, Big Chalupa, and Ain't Got No Time. Alright, starting from only these two equations. Now, I'm never going to ask you to reproduce this, but I do think it's important that you see it at some point. Okay, so let's start with the easiest one to derive, which is Old Faithful. So Old Faithful comes straight from this equation, right? It comes straight from the acceleration equation. So I can just say A equals delta V over delta T, but we're going to say that delta V is equal to V minus V naught. And then to simplify these equations, we're always going to assume that we start from time equals 0. And if I start from time equals 0, then instead of saying delta T, I can call it regular T. So now if I just take these two parts of the equation, I have A equals V minus V naught over T. Then I'm going to multiply both sides by T. In algebra, if you do something to one side, you can do it to both sides. That's going to cancel out the T's, and then I have A times T equals V minus V naught. I'm going to add a V naught to both sides, and then I have V naught plus AT equals V, or if I write it the way I wrote it yesterday, if I just flip-flop this, I have V equals V naught plus AT. Yay. I don't know if you've ever seen this this term QED before, but this is the mathematical terms. It stands for the Latin phrase quod erat demonstrandum, and what it means is that which was to be demonstrated. In other words, it means that I proved what I was set out to prove. Right? I proved where Old Faithful came from. All right. Well, the other two get a little bit more complicated. So now let's look at let's try and derive Big Chalupa. What we're going to do is we're going to start with something that sounds silly. We're going to start by saying that the average velocity is equal to the average velocity. You can say that, right? I imagine you can. That's just true, right? It's a true statement. Okay? So then I'm going to say, okay, what average velocity we know is equal to delta x over delta t, right? So average velocity is equal to delta x over delta t. And here's what I'm also going to say. I'm going to say that if you don't have to write this down, but if you imagine a velocity graph, and if I have a constant acceleration, and I have a starting time and an ending time, I'm going to say on average, I'm going to be going at a velocity that's halfway between the starting and the ending velocity. So in other words, I'm going to say that average velocity can also be said to be equal to V naught plus V, the initial velocity here plus the final velocity divided by 2. That's going to be the average velocity. Okay, so I'm going to start there, and then I'm going to say, okay, well, I know what this V is equal to, right? I can say this V is equal to Big Chalupa. So instead of writing V naught plus V, I'm going to write V naught plus AT. Right, so I just plugged that into here, and then I'm just going to rewrite the rest of the equation. Okay. So from there, what I'm going to do is I'm going to I'm going to kind of, I would like to factor out this 2. So what I mean by factor out the 2 is I'm just going to say, like, okay, I know that I've got V naught plus AT, right? Well, if I take away these parentheses, I can say V naught plus V naught is 2 V naught plus AT. So I have this equation. I'm just going to grab a separate sheet of paper here. And then what I'm going to do is I'm going to kind of carry this 2 over to each term, right? So 2 V naught divided by 2 is V naught, and then AT divided by 2 is 1/2 AT. Okay. Now I got to finish this out on this side of the equation. I'm going to say delta x is like saying x minus x naught. And again, I said that if I start at t equal to 0, I can say that my delta t is equal to t. Then I'm going to do what I did before, and I'm going to multiply both sides by t. So then I have x minus x naught, because my t's canceled out, equals v naught t plus 1/2 AT squared. I can add an x naught to both sides to cancel out, and then if I just rewrite it the other direction, I've got x equals x naught plus v naught t plus 1/2 AT squared. So that is where the big chalupa equation comes from. Alright, we got one more to derive, and that's the ain't got no time equation. This one is the most complicated derivation. You might wonder, how do I know how to do these steps? Because I've been doing it for a long time. Again, these are things I'm not going to ask you to memorize these equations, and I'm not going to ask you to do these derivations. I just want to show you where they come from. Okay, so here's the most complicated derivation is the ain't got no time equation, and what I want to do is I want to start again with Old Faithful. So I'm going to start with Old Faithful and say v equals v naught plus AT. And just because I can, I'm going to square both sides of this equation. And we're going to watch what happens. Well, if I square v, v squared is v squared, right? And then if I square this thing, I got to do a FOIL, right? So if you remember, a polynomial squared should be a squared plus 2ab plus b squared. So this is what, if you FOIL that out, this is what you get, right? Okay. Now what I'm going to do is I'm going to factor out a 2a from this part of the equation, and I'm going to do it, and then you'll take a look and make sure that you understand where I got it from, right? If I factor out a 2a from this term, what am I left with? Should be left with v naught t, right? And if I factor out a 2a from this term, I get 1/2 AT squared. Now, if you have no idea how I did this, what I'd like you to do is I'd like you to distribute the 2a across. If you distribute the 2a across these terms, you should see that this line is equivalent to that line. All right. So then, does this look familiar to you? This looks an awful lot like what we had up here, right? V naught t plus 1/2 AT squared was equal to x minus x naught. So now I've got v squared equals v naught squared plus 2a x minus x naught. If you look at your notes from last time, that is the ain't got no time equation. Again, I'm never going to ask you to derive these, but I just think it's important that you have seen the derivations so that you know that they came from somewhere. And also, like I said, I think it's cool to start from some pretty simple starting points and be able to derive complex equations out of them. All right, that's what I got.